Where's the image? All right, hello class. Mr. Pettibone here. Um, and a couple of news announcements. So next week is the last week for seniors. Um, we do have seniors in the class. So I think what I'm going to do is just next week is going to be the last week for IB Physics SL. I am going to give you one more short quiz on this topic on astrophysics, and then that'll be it. So Dr. O'Connor recommended not really giving a final exam, like a final exam. So anyways, I think week after next, I might just have a check-in for juniors in the class, and yeah, so I'll give you some points for that or something. But technically, I'm supposed to continue one additional week for the juniors. But if you don't tell, I won't tell. Shh. Okay. Hey, Ben. So today we're going to talk about galaxies. All right. And what is a galaxy? It's a gravitationally bound collection of stars. Stars, gas, dust, etc. Okay? Um, Typically, galaxies are going to have of the order hundreds of billions of stars. A lot of stars. Okay? Typically, they're going to be tens of light years across. And in fact, I misspoke yesterday. Our own galaxy is, I said 15,000, it's actually 150,000 light years across. So it can definitely be many tens of light years across. And so I'll put a plus there. And just so you know, our own galaxy is called the Milky Way. Why is it called the Milky Way? Because if we had lived in, prehistoric times, when it was nighttime, it was really dark, and you could see many more things in the night sky than we can currently see because of light pollution. And so the stars within our galaxy made a clearly visible strip across the night sky, and it was white. It looked like milk, so they said, "Oh, it's the Milky Way." All right. So galaxies have many different shapes called morphologies. Okay. And so if you look in the lower left-hand corner of the screen, you can see the different morphologies of a galaxy. So some galaxies are spiral galaxies. In fact, that's what we think the Milky Way is, or that's what the Milky Way is. It's a spiral galaxy, which means it basically looks like a whirlpool. And there's some variations of that. There's barred spiral as well, which looks like a spiral galaxy, but it has sort of like the center of the galaxy has more of an oval shape to it. One of the things you'll notice about spiral galaxies is they have sort of like dark bands. And those dark bands are clouds of dust. Okay? So it's dust, gas obscuring the light from the stars. Okay. Another thing you'll notice is that the center of the galaxy, of the barred spiral in the spiral galaxy, tends to be yellow, and then the outside of the galaxy tends to be blue. Okay. And what that means, according to the stellar classification scheme, blue stars, that's those O-type stars. Okay, so the center of the galaxy, the core, the so-called core of the galaxy, has very few O-type stars. They're older. The center of the galaxy is made up of older stars that tend to be yellow or redder. And then the outside of the galaxy, that's where all the gas and dust is. And that gas and dust is continually making new stars. And some of those are O-type stars. So it gives the outside of the galaxy this, bluer color. The time it takes to orbit a galaxy is a long time. It's something, of the order of 1 billion years. If you were in orbit around the galactic center, it's about 1 billion years to go around. Okay. Another common type of, oh, by the way, if you look in the upper right-hand corner, that spiral galaxy is definitely interacting with a second galaxy. So galaxies do collide and coalesce into a bigger galaxy. But one of the interesting things about that is true about galaxies is that they're mostly empty space, right? If we think about the size of the sun compared to the distance between the sun and another star, galaxies are mostly empty space. So if two galaxies collide with each other, the probability of two stars actually hitting each other is basically zero. So, you're going to see the galaxies change shape, and you might have two stars that go into orbit around each other and form a binary star system, but for the most part, there's going to be no direct collisions between stars when they collide. I'm sure it has happened in the universe before, but it's a really rare event when galaxies merge. When galaxies merge, they might form what's called an irregular galaxy. I just noticed that in this picture that I copied, irregular is spelled incorrectly. But an irregular galaxy is just one without a consistent shape. Okay? And then some other types of galaxies you might see are elliptical. And elliptical galaxies, and its related galaxy lenticular, you can see that, first of all, they're almost entirely yellow. So these are older galaxies. They've got, not a lot of O-type stars. So these are mature stars in these galaxies. And they have a much more sort of uniform pattern. One of the things that just amazes me about pictures of galaxies is it literally looks like a cloud, but each point of light within that cloud is a star. So it's a, if you think about a cloud, looking at a cloud, and if you were to zoom in on the cloud, it's a bunch of water droplets, right? Many water droplets. If you zoom in on a galaxy, the thing that make up the shape of the galaxy are literally stars. There's so many stars that it makes, you can't even tell that there are stars. There's so many of them. I did want to show you, I'm going to show you some other pictures here. Give me a second because it's going to have to show a different image. Okay. So this is another really famous galaxy. It's a spiral galaxy. It's almost like, to me, it looks like a spiral galaxy on top of a elliptical galaxy, but it's classified as a spiral galaxy, and this is called the Sombrero Galaxy. And notice how the spiral part of the galaxy is edge on. Okay, so not all galaxies have the same orientation. All right. Some galaxies are, the disk of the spiral galaxy is facing us so that we get a nice image of the top of the galaxy. Other times they're edge on. And if you look at this image more closely, it's really interesting because you can actually see other galaxies. See, there's another galaxy right there. There's some galaxies. There's a galaxy. So there's tons and tons of galaxies in this image. If you look right here, that is a star. That's an individual star. That's not a galaxy. How do I know that? Because individual stars make this cross pattern. And that's, if you were to actually look at this image with your naked eye, you wouldn't see the cross pattern. The cross pattern is an artifact of the telescope imaging process. So if the telescope images a point source of light, it makes this cross. They're called diffraction spikes, and a lot of cameras have them. If you watch a TV show and they have an image and there's like a lamp, the lamp might have diffraction spikes. Okay. I got some other pictures I want to show you. All right, let me get to this picture. Here's another spiral galaxy. Not quite as edge-on as the Sombrero Galaxy, but one of the things I want to point out is if we look in the lower left-hand corner of that galaxy, we can see an individual star. Okay? So you might think that that individual star is sort of like along the line of sight between us and that galaxy. So that star is kind of photobombing the image. But this is actually a supernova within that galaxy. So the galaxy extends out, and this is a star that's orbiting that galaxy. And that star went supernova. And you can see that the star is as bright as the entire galaxy itself. So basically if astronomers had looked at this image a couple months before, they wouldn't have seen that individual star because it was not bright enough to be resolved by itself. But because of the supernova, it's now as bright as the entire galaxy. Okay. So I thought that was a cool image. I've got another image for you. I got a lot of pictures. That's why I was late getting started today, because I was searching all the images. This is a really famous picture from the Hubble Space Telescope, and it's called the Hubble Deep Field. And we can see one individual star in this galaxy. In this picture, it's right here. But everything else is galaxies. So that, oh, actually maybe 2 stars. That looks like a star right there. So basically what they did with the Hubble is they were just like, we're going to take a picture of a blank section of the night sky, okay? So they were just like, all right, that section of the night sky looks blank, and they just zoomed in with the Hubble telescope as closely as they could, and this is what they saw, and it's literally just filled with galaxies. I mean, there's got to be hundreds of galaxies, probably more like thousands in this image, okay? You can see that many of the galaxies are a deep red. So that probably means that that's a galaxy that's really far away because it's redshifted so much. I don't know that galaxies naturally have that color, so I'm pretty sure that these galaxies that are just sort of a deep red are actually being redshifted due to the Doppler effect and the expansion of the universe. But you can see, if you look at this close enough, you can see spiral galaxies, you can see elliptical galaxies, you can see irregular galaxies. There's just tons and tons of galaxies out there, okay? So I think that's a really cool picture. One of the other things that's inside galaxies besides stars are something called nebulas. Nebulae is the plural. And a nebula is basically a cloud of gas and dust. Okay? So let me show you a picture of the most famous. I'll show you the most famous nebula. Pull it up here. So this is called the Pillars of Creation, and it's a nebula within the Milky Way. And so a lot of times nebulae are called stellar nurseries because this is the kind of cloud that stars will form in. Okay, so if there is any kind of density or regularity in this cloud, then it's going to start to gravitationally collapse and turn into a star. Okay, I believe that the leftmost pillar is something like 7 light years tall. So this is a really big cloud. And many stars can form inside it. And of course, as stars form, it's going to suck up the material from the nebula, and then the nebula will go away. So why are there nebulas in the first place? How did they form? Well, what happens is stars are being born all the time, and stars are dying all the time. And so, stars go supernova, for example, and it sprays out all this new gas and dust out into the universe, which, it happens enough times and you have another nebula, which then collapses to form more stars. Okay. I wanted to show you an image of a nebula that that formed from a supernova. So let me pull that up here. So here's a nebula that formed from a supernova. Okay. So yeah, and you can basically see it's a shock wave that's just traveling out away from where the star was. So maybe there's a black hole in the center of that. Okay. Okay, so I got some questions here. Hey Akshay, hey Spicy Pepper, hey Jackson, hey Christian, hey Michael. So let's see. Why do some of the galaxies look like there's a huge sun in the middle? That is the core of the galaxy, and it's made up of older stars that are older stars tend to be yellow or redder, and so that's why it looks yellowish reddish. But the important point is that that's not a huge sun. That's many billions of stars that are light years apart, but they're so far away that you can't even tell the individual stars apart. Okay. Akshay asks, how could an individual star exist without a galaxy holding it in? I'm sure that there are stars that that are not bound to galaxies, that have been, through interactions, gravitational interactions with other stars, they could possibly be flung out of the galaxy. So we also think there are planets that have been flung out of their solar systems, and those are called rogue planets. So they can exist. You just need a cloud of gas and dust to collapse, and then you've got a star. So, all right. One thing I wanted to talk about is that most galaxies, actually, I take that back. We think all galaxies have a black hole in the center. Okay, so we actually think that a black hole could be the thing that, so the whole formation of galaxies and stars. How does a galaxy form? Well, you have a really big cloud of gas and dust that collapses, and then that cloud sort of collapses into smaller clouds, which then become the stars, right? So it's the same process as star formation, but with a galaxy. And we think that the thing that starts the galaxy forming, that starts the gravitational collapse into a galaxy, is a black hole. Okay? So these black holes that are at the center of galaxies are really old, and they are incredibly massive. So we say that they are supermassive black holes. So when I say supermassive, I mean that these black holes could have masses of the order 10 to the 6 solar masses, even 10 to the 9th solar masses. So a million suns worth of material, a billion suns worth of material has been eaten by that black hole. Okay? How do we know that? How do we weigh a black hole? We watch the stars that are orbiting it. Okay? And it's interesting. We watch stars orbiting black holes, and it looks like they're orbiting nothing. Because you can tell that it's orbiting something, but when you look at the center of the orbit, there's nothing there. And so you can deduce that it's a black hole. The black hole at the center of our galaxy is called Sagittarius A star. Why is it called that? Because the direction of the galaxy, the galactic center, is in the direction of the constellation Sagittarius, and around the black hole there is X-ray emission, or maybe it's radio emission, and so that's how they discovered it. So it's just the A star means a source of electromagnetic radiation. Okay. So I wanted to, the last thing I wanted to talk about is a bit of a mystery. Okay. So how do you weigh a galaxy? Okay? How do you weigh a galaxy? How do you know how much mass it has? Okay? Well, what astronomers have done is they say, gee, um, they say, gee, uh, most stars are like the sun. The sun is a pretty average star, okay? So what if I assume that every star within a galaxy is just, and you can get better estimates by being more precise, but you can get a ballpark estimate of the mass of a galaxy by saying, all right, every star is basically like the sun. We know what the luminosity of the sun is. So what we do is we look at the luminosity of the galaxy, okay, the entire galaxy, and we say, well, it is n times the luminosity of the sun. So then we can figure out the number of stars in the galaxy by looking at the luminosity of the galaxy and comparing it to the luminosity of the sun, and the ratio of the two tells you the number of stars in the galaxy. So that's how we know there are hundreds of billions of stars in a galaxy. Okay? Then what we do is we say, well, if the sun is an average star, what if every star in the galaxy has an average mass that's the same as the mass of the sun? So then we deduce that the mass of the galaxy is n times, so we used the amount of light coming from the galaxy to deduce the amount of stars. Then we assume that every star is like the sun, and we multiply the mass of the sun by the number of stars, and we get the mass of the galaxy. Okay? So that's how we can estimate the mass of the galaxy. Now, there are lots of different ways to measure the mass of a galaxy, but this is just one of them. Okay? Now, this makes an important assumption. Okay? And this assumption is certainly really good for our own solar system. If we look at the solar system, more than 99% of the mass of the solar system is within the sun. So if we took all the mass that is not in the sun and we clumped it together and we compared that to the mass of the sun, it wouldn't even be 1% of the mass of the sun. Okay? The sun is that massive. So what we're assuming basically when we use this method of weighing the galaxy is that anything, everything that makes light is all the massive stuff in the galaxy. Nothing that's dark has any significant amount of mass. Okay? We're saying that light is equivalent to mass. All right? Akshay asks, is our sun a good representation for the average star? Yeah, it's pretty good. If you were trying to make a really precise estimate, you would do like some kind of a weighted average of all stars. So, you would say, 10% of stars are O-type stars that have this luminosity, and you know what I mean. So you would do a more precise with the distribution of stars within a particular galaxy. Okay, so this is one estimate of the mass of a galaxy. Then there was an astronomer. Her name is, or was, I think she passed away, Vera Rubin. Okay. Female astronomer, girl power, women in STEM. And so what she was doing is she was looking at spiral galaxies, okay? So let's say here's a spiral galaxy that we're looking at that's edge on, okay? And the galaxy is rotating, right? So there's a galaxy, or there are stars in the galaxy on this edge that are moving towards the observer, and there are stars on this edge of the galaxy that are moving away from the observer because it's spiraling, right? Towards you, away from you, towards you, away from you. Okay. So what Vera Rubin did was she used the Doppler effect. To measure the speed of these stars with respect to the galactic center. Okay? So she used the Doppler effect to see how fast are these stars orbiting the galactic center. And these are the stars that are on the outer edge. Now, if you recall, here, let me... if you recall, we learned Kepler's law, which said that gm t squared equals 4 pi squared r cubed. We use that to determine the period of planets and so on. We can actually rewrite Kepler's law, and what we get is that the velocity of an orbit is equal to square root of gm over r. Okay? So what Vera Rubin did was she applied this equation, Kepler's law, the exact same equation that you guys learned in class. And so she got the speed of the star from the Doppler effect. So this is the speed of the star that is orbiting. And then based on how far away the galaxy is and how big it appears, she could determine what is the radius of the star's orbit. Okay? So the velocity of the star comes from the Doppler effect. She gets the radius of the orbit from the telescope. Okay? And use that to determine the mass of the central body. Now, what is the central body that the star is orbiting? The central body is the entire galaxy. So this is the mass of the galaxy. Okay? So, now if our assumption that bright things provide most of the mass in a galaxy, you would expect that these two methods of determining the mass would give the same answer. Okay? But what Vera Rubin found was that this method of determining the mass of a galaxy always gives a greater mass than the mass calculated with the amount of light coming from the galaxy. Okay? This method of determining the mass of the galaxy always gives a greater mass than the mass calculated with the amount of light. And it can be significantly more. So we're talking about it can be double, triple the amount of mass. So they were like, what? So what that means is, so the conclusion is there is a significant amount of mass in a galaxy there's a significant amount of mass in a galaxy that is not visible. Okay? And this mass that is in the galaxy but not visible has been given the name dark matter. Knock it off! Okay? So it's called dark matter because we can't see it. So, it's a great mystery. What is dark matter? We have no clue. If you figured out what dark matter is, it would be an instant Nobel Prize. Okay, this is one of the unsolved problems in astrophysics. But whatever it is, and by the way, we know that it's not black holes. Most people think, oh, it's going to be black holes, right? But the thing is that black holes bend light. So when light passes by a black hole, it curves it. So if dark matter was made up out of black holes, maybe galaxies just are filled with black holes everywhere. All those black holes would distort the light coming from the galaxy in a way that has a signature. So we would be able to say, oh, the light from the galaxy is distorted in a manner that's consistent with there being a lot of black holes. But we don't see that. Okay? So what we think most likely is that the matter that makes up dark matter is probably now some people think that the theory of general relativity is just wrong. That could be it. That general relativity is not correct. Now every direct test of general relativity has been correct, has shown that the theory is correct, but this could be something where if you get on the scale of galaxies, somehow general relativity isn't right anymore. But the evidence seems to be pointing towards the fact that dark matter is composed of particles that are a lot like neutrinos. So you might remember neutrinos only interact via the weak force. So we think that they are neutrinos, but like a massive version of the neutrino. So we actually call them WIMPs, weakly interacting massive particles. So you can't see them, they hardly interact with anything, but they have a lot of mass, and so they can pull things in stars and galaxies. But we don't know for sure. So it's just really weird to us that actually most of the mass in our galaxy appears to be dark matter, and we can't see it, we can't detect it, other than through the fact that it makes stars orbit differently than they should. So it's a big mystery. So as I said at the beginning of the lesson, next week will be our last week of classes. We'll have one more quiz, and furthermore, what else did I want to say? Furthermore, we will not have class tomorrow because we're only doing 4 days a week at this time. Okay, so I will talk to you on Monday.